Okay, so I think we are pretty complete now, so let's start our last day to make effective use of it. First of all, following our discussion yesterday, I updated the schedule on the course website. Saturday will work from my side between the time window here locally, 7:30 p.m. to 9 p.m. And so let's leave it at that. At that time we'll do all problems on the problem set on DSGE models. That's now also in complete form on the course website. And I'll talk a bit also about the sample project. That's not yet on the course website, but that I'll have posted prior to that class that we'll have online. And that will be per se, based on the problem sets, perhaps slightly augmented questions in part, because you're not going to be operating under huge time constraints. Some time constraints, 3 days is a time constraint as well, but not as high time constraint. So, but anyway, we'll talk about that sample project, and also I will propose in that online session. I'll try to make sure I have it posted a couple of days in advance so that you can also take a look at it if you want to ask questions about that as well. But of course, I don't expect that you'll have solved the sample project by the time of that online session as well. And again, some of it is going to be literal repeats of what's on the problem sets in the images. So much for course organization, right? I trust everybody is fully aware of the dates for the project, the Wednesday to Friday before the programming languages course will start, and you have the time all the way from the Monday in the week prior to that Wednesday to prepare. And if you want to get started preparing, of course you can also do right after the Aliasas exam starting Friday evening to have an additional 2.5 days. Just joking, don't. Take it as any pressure on you. You know best how to do things and how to organize the way that you want to do things. So just do that what works for you best to make sure that you're adequately prepared.
Sorry, just for clarifications. So it means like we have like a period of about like 1 week to revise the material. Then you will start posting the project questions, and then we have like 3 days to submit it, right?
Yes, 1 week and 2 days, I would say, from Monday of the first week to the end of Tuesday of the second, and then I'll post the project Wednesday. I'll probably, to make it feasible that you really have the whole working day from your side, I'll post it at the very end of my day Tuesday. So if you get up by 4 or 5 in the morning, it'll probably already be there. And then I think we'll make the deadline 23:59 local time on Friday.
Understand, yeah.
Is that fine? Okay, so if that covers the questions on the organizational aspects, I would say let's start our substantive work. And for that, we'll go to the problem set and want to work on that first problem on the problem set that looks at the household problem within our new Keynesian DSGE model, where the household maximizes that expected present discounted value of lifetime utility with a slight variation on the utility function that we had in the slide, so that also the consumption portion here is in the problem set like we had it in the RBC model, constant relative risk aversion, budget constraint, pretty much in line with what we have in the lectures, except that there's here no dividend specified. And then again, we have, like in the lectures yesterday, a preference shifter that is to be viewed as a demand shock for this economy, right? That households in some periods, because of changes in preferences, will demand less consumption, less leisure. So we need to obtain the optimality conditions and then log linearize around the steady state. Per se, we have two optimality conditions, right? One which is intratemporal and one which is intertemporal. So if you wished, we could also split it up. So that two of you could work on this problem, one on the intratemporal allocation between consumption and labor/leisure within any given period, and the other one could work on the intertemporal allocation of consumption. Okay, so I don't need to pay. Okay, I just want to make sure you didn't pay for it and then pay for it. So that would be my suggestion, right? That we could split it up, but if one of you wants to do the whole thing, then that's perfectly fine as well. So, eagerly anticipating hands going up.
I believe Mr. Ian has promised, has wanted to volunteer.
Some are pointing at you. But don't just, if you look around, some are pointing at you. You want to do it? Okay. And which one? With the in-period intratemporal consumption labor decision or the Euler equation? You can try all of it. Sure. If we don't have a second volunteer, then so that's the intratemporal one, right? And then this one, the Euler one, you need to someone else. Intratemporal, yeah. Okay, so please go ahead and do that. Yeah, that's fine. And then we'll find someone else who does the Euler equation. Yeah. So a second volunteer still invited to obtain the intertemporal optimality condition, the Euler equation, and then log linearize that one. Otherwise, we can also postpone that either to the beginning of the afternoon or to the online session.
Sorry, that you need to do the Taylor approximation, right? For that part? For the...
And I think then the air conditioning is a bit loud.
So for the Euler one, because I haven't done it, but just want to check if the direction is sound for that.
So you want to write it down?
No, I'm still getting stuck. But is it supposed that we have to use the Taylor approximation on that part?
So you get, pretty much a very similar Euler equation, right, as we had in the slides yesterday. Just that the functional form on the evaluation of consumption utility function is CRA, not log consumption. So you obtain the nonlinear Euler equation, and then you take the first order Taylor series approximation of that around the steady state, obtained by weighting times output across both sides of the Euler equation. That would be the procedure. But I think for now we don't have really a volunteer for that one, so let's see whether we have one at the beginning of class in the afternoon, and if not, we'll postpone it to the online session. It's a little bit more involved in the derivation, specifically when you log linearize, because it's quite quite an expression, right? So doing that ad hoc may be a bit too much. But hopefully we can do one on labor versus leisure intra. Anyway? Yeah, okay. Okay, round of applause for the work done on the whiteboard, which does state the Taylor series expression, right? That if we have a function of two variables, x and y, that we want to take the value of f evaluated at some point x0, y0, and add to that the sum of the partials of f with respect to x, with respect to y, each one of them multiplied by the deviation of x from that point about which we do the expansion, the point for x is x0 and for y, y0. And then it looks at a function in x and y, takes those partials and evaluates it. That's fine. Maybe we had a slight misunderstanding. I thought you're also going to do, though, the optimality condition of that with respect to C and N. Combine those into one. Right? If you think back to the optimality condition that we had yesterday afternoon, right, that we'd obtain that optimality condition, how to allocate in the current period between consumption and labor/leisure as a function of the real wage. Of course, here the expression would now be a little bit different, because in the problem set, right, we'd instead have that the evaluation of consumption within the utility function is CRRA, right? And so that would be, in terms of the optimality condition, therefore, the same as what we had in the context of the RBC models yesterday, the optimality condition in 8. Right? So that's the one that we'd also get here for the problem set. And now what I'd like to see is, using this specific expression, rather than the one you chose here, to do the first of the Taylor's expansion, so that we get something that is linear in consumption, linear in labor hours, and expresses that as a function of the real wage. Do we have a volunteer to do that part as well? In principle, right, you do the same thing as here. X is C, Y is N. You log linearize with respect to C and N as a function of the real wage. But if you don't have an immediate volunteer, I would suggest let's postpone that to the afternoon too, and if that's too early, to the online session.
Okay.
Yeah, equation 8, to specifically log linearize. Applying the rules that you wrote down, but applying those rules specifically to that equation 8. Want to do it? No? Okay, sure. But you can take that as quick. Right now we go to log linearize this expression. Right, but we haven't done it here yet, right? So we have to do it from scratch now.
C star?
Yeah, whatever you prefer notation.
Yeah.
Use the notation, use the
I can
notation.
send it right.
Okay, another round of applause for deviations on both sides. So let's start on the right, and then we go to the left. So there's various ways how you can actually do the Taylor approximation. You could, of course, in principle also say, rather than following the approach that's on the whiteboard, that I take this whole function, right, and take partials with respect to zt, zt, zt plus 1, ct plus 1, rt plus 1, pi t plus 1, and write that big Taylor's approximation. At first I thought you would do that, but this is less work and gets to the same result in the end. So I commend you for doing that. But if you say I would have taken the Taylor series expansion for this whole thing, I would have found that not implausible from the instructions that I gave you. But this is very fine because it saves a lot of work at the end of the day, right? Basically it says, let's look at each and every expression and realize once we have taken a log of this stuff, right? This is basically already, of course, linear in the logs of zt, zt, zt plus 1, zt plus 1, rt plus 1, pi t plus 1. Let's now replace the log of the variable by what is the log of that variable at the steady state? Last, what is this? The percentage or fractional deviation of the variable from a steady state. Right, and now plug in. And then you realize once you plug in, you of course have a lot of terms in steady state expressions, but effectively they cancel out. Right? Either you take the difference or you just plug that back in, this minus this, plug that into the previous expression, it just drops out. So that at the end, you both just have an equation left. In each and every variable, consumption contemporaneously, reference shock contemporaneously, consumption in T plus 1, preference shock in T plus 1. This overall, of course, is the real interest rate, right? We could also, if we wanted to reduce this to just one variable, we could alternatively also think about calling this lowercase rt plus 1 hat, right? Because in essence we work on the interest rate. Then we'd have saved a little bit notation. So I didn't see that before. Of course, here we had the conditional expectations operator, right? So please do not leave it out, right? So what we have here is the conditional expectation at t of what is the fractional deviation of consumption at t plus 1 from its steady state, and of course for all of those, right? The conditional expectations operator. You had it, right? I just didn't see at first too that you didn't bring that to the next one. But that's the log linearized form. Right, so it basically says I have expressed everything in a linear form in those deviations from the steady state, where if you didn't hear it before, they asked me, can I use the more compact notation that x star is our steady state, right? And so that is our log linearized form. All right, now if you take that to the other side,
I write a bit because the C and the Z is kind of obvious, but the R here is like you need to as recent when you do it, and then you define the R hat here, because my R hat is not like RT plus 1 minus R star, but divided by
right, but
1
we know why, because this is a 1 plus. This is approximately the same as this fractional deviation. If you want to write it down for the benefit of everyone else so that they see what you did, fine. from my perspective, if you want the solution as is, I would understand,
Yeah.
but maybe you want to write it down so everybody is happy with that part as well.
I just wanted to explain it to you.
Yeah, okay.
It's like, it's a bit different from the other way that we.
That's right. But it's per se exactly the same thing in the end, right? It's the fractional deviation
Yeah.
of the interest rate in the period of the steady state. Okay. So any other questions on the right hand side on what we have here? If that's not the case, then let's go to the left, and on the left we have in the notation, right, of the problem set, the derivation of this intra-temporal optimality condition, allocation between labor/leisure and consumption. The typo there was already corrected. So what if I now wanted to make that log linear as well? But if you think about what we have on the right-hand side, if you did the same thing here, first took the log, then approximated the log by the log at the steady state plus the fractional deviation, right? All the steady state stuff would again drop out. So what would this become? Phi, and now let me use the same notation as we have over there. Phi times nt hat plus sigma times ct hat is equal to, that we denote this just as lowercase w, right? So that lowercase is the real wage. If uppercase w is the nominal wage, so this is equal to the fractional deviation of the real wage from steady state. Right? With exactly the same steps as we had on the other side. It's just here we don't have expressions in t plus 1, so there's no English expectations operator because everything is stated time period t. And then that is log linearized. That's it. Okay, so practice it with the other optimality conditions. In the end, you'll get the linearized, log linearized version of the model anyway in our mod files. Right? Remember, for example, yesterday when we had this mod file for the RBC model, you actually had in there already log linearized equations. Right, so you can check back on all the equations and make sure that you can derive all of them from our nonlinear optimality equations. Okay, so I think that's our first question on the problems that on the DSGE models. The remaining ones we cannot do yet. We'll need more material. But by the end of the day, I'm confident we are there, and we can do the rest of the problems then also, at least for that online session next week. If there's no further comment, query, question on that, then I'd say let's use, of course, the remaining 40 plus minutes that we still have to head back to the lecture slides. What we want to do at this point is, right, having discussed households, and we basically just, of course, in essence, reviewed also what we had done yesterday looking at the household optimization problem by log linearizing those optimality conditions of the household, log linearized 9, log linearized 13. So we now, within this new Keynesian DSGE model, have reached the stage where we can discuss firms' behavior. So let's turn to that. In the RBC model, of course, this was a rather simple setup, right? There was a firm that had a conductive production function and maximized its profits. Profits were a static optimization problem, and the firms were operating under perfect competition. So in the end, the price level of the economy was equal to the marginal cost of production for the firm. In the new Keynesian DSGE model that we'll study here, things are going to be a good bit more subtle and also demanding in the derivation. Why is that? Because one of the criticisms, I would say, of the default real business cycle model is that everything is operating under a perfect competition. That seems a bit unrealistic, right? That it seems much more likely that firms operating in an economy have some degree of pricing power, and that the price deviates from the marginal cost to a marker that the firms charge on marginal cost. That's the first thing. And the second thing is that within this new Keynesian DSGE model, we will now also allow for a distinction between a final good, that is the aggregate output, and the variety of intermediate goods, so that we also have different goods and services, and in that sense, certainly also go beyond the representative firm setup. So let's start with the final output, right? That's the aggregate output YT. That is simply specified as being a function of intermediate goods that the final goods producing firm uses as inputs. Right, we'll come to these intermediate goods producing firms in just a minute. We haven't seen them yet. All that we are saying in 14 is if we know what the intermediate goods producing firms produce as output, then there's basically going to be an aggregation of these intermediate goods into a final output. And to keep matters simple, this aggregation doesn't involve labor hours or any other resources, right? So this is kind of a wholesaler who just converts the intermediate goods into a final good. Because if you said, is that the most realistic form of aggregating intermediate goods into a final good? For sure not. This is an abstracting device, right? That we convert those intermediate goods, YT, into final output using the aggregator in 14. This is not really a production function. This is just an aggregation device, an abstracting assumption. What we presume is that there's a continuum of intermediate goods producing firms abstracting on the unit interval, right? Because if we have a continuum of firms on the unit interval, then it basically means we have an unlimited number of intermediate goods producing firms, and so we can restrict that to the unit interval. But again, that is just an abstracting assumption. Right, of course, a normalization in a way that we put all of these intermediate goods producing firms on the unit interval. I don't think of that in terms of having any analogy in the real world economy or the like. Again, this is just an aggregator, right? A device to convert from the intermediate goods that were produced. And once more, we'll still need to talk about them. We haven't talked about those yet, into a final output. Now, this parameter lambda f in the aggregator is basically going to govern the degree of substitutability between different intermediate goods. And And what you can probably already imagine, right, is if I produce a good, an intermediate good, that is not readily substituted for by other intermediate goods, then I'll have more pricing power. Because there's nobody else who can do the thing that I can do, so I can charge a higher markup. And we'll see that lambda f is indeed also going to govern the pricing power of those intermediate goods producers. But formally in the aggregator, right, it's just going to govern the degree of substitution between different intermediate goods. Now, if you maximize output from 14, what you will obtain for any given expenditure level that the final goods producing firm has, right, was an expenditure level across all intermediate goods producing firms aggregated. They purchase YIT in terms of the amount of the intermediate good and pay price PIT for it. Right? And so if I integrate across all these intermediate goods producing firms, that's the total expenditure level that the final goods producing firm will have on the intermediate goods. So, without proof here, but I think you might want to do the algebra just to be sure, to understand. It's not heroic algebra. Maximize 14 subject to the constraint that we have a given expenditure level. And if you do that, you obtain 15, which is in essence what is demand for the I intermediate good by the final goods producing firm. Intuitively, the demand for the I intermediate good is a function of how much aggregate output do we want to have. The more aggregate output we want to have, of course, ceteris paribus, the more is going to be demanded of each intermediate good. Right? That seems almost trivial. And what is the second term? In terms of interpretation, almost trivial too. What else does the demand for the intermediate good depend on beyond the aggregate level of production? The relative price of the intermediate good relative to the aggregate price of output that we know as PT. And so, of course, the larger the price of the intermediate good, everything else equal, including degree of substitutability, I will, of course, want to demand less of the intermediate good. Right? That's the demand function for the intermediate good. Interpretation, again, I would say, almost trivial. You demand more of the intermediate good, the more you want to produce in the aggregate, and at the lower the price of that good relative to the aggregate price level. Now, if you integrate from the expression that you get when you plug 15 back into 14, while you plug 15 back into 14, you can basically make 14 equation in PIT and PT, right? And so PT is also the aggregate price level, is the appropriately aggregated function of all those individual price levels. That's all that 16 says, nothing more to be told, right? But we have also obtained the aggregate price level of this economy. But of course, at this point, just as a function of PIT, and we don't know the PIT thing, right? We have to turn to the decision-making problem of the intermediate goods producing firm, of course, to understand how are they going to price their goods that they produce. But once we know that, right? Once we know YIT, once we know PIT, we can calculate from 14 aggregate output, and we can calculate from 16 the aggregate price level. Now recall I just said a minute ago, this parameter lambda f in this aggregator is not just going to measure the degree of substitutability between different intermediate goods and aggregating them to a final good, but it is also measuring the pricing power of the intermediate goods producers. How can you see that? If you look back to 15, right? 15 was our demand for the ith intermediate good. What happens in 15 if we let lambda f become large? That is, in the limit, let lambda f tend to infinity. Then in the limit, what does this converge to? Then the 1 is irrelevant, right? It converges to minus 1. If lambda f tends to infinity, this converges to just minus 1. And what is that situation then? If that is minus 1, right? This is really becoming pt divided by pit. The demand for the ith good is relatively priced in elastic. If, on the other hand, lambda f is close to unity, go back to 15, right? If lambda f, we started off from it being very large, from above converges towards unity. There was 1.01 or 1.001 or something like that, right? Then again, of course, this is negative, but a very small number as lambda f approaches 1 from above. And what does this ratio tend to? Infinity. Right? That this will tend to infinity if lambda f converges to 1 from above. Let's take an example. Maybe not just 1.01 or 1.001 or 1.00001. And then this is basically almost 0. The negative sign, and this is still 1.001 divided by 0 tends to infinity. Right, so if lambda f approaches unity from above, what do we have in that situation? We have no pricing power of the ith intermediate goods producer, and that of course corresponds to the situation where the intermediate goods are close to perfect substitutes. Right, so lambda f is going to be simply determining what is the degree of pricing power of the intermediate goods producer. As lambda f was tending to unity from above, we are reverting in essence to a fully competitive setup for the firms, but we have little possibility that as lambda f increases from 1, that we tend in the extremum case where lambda f tended to infinity, you turn to basically having a monopoly power of the intermediate goods producer. Not a quite flexible setup, right? In terms of having different degrees of imperfect competition, could range all the way from monopoly pricing power back to as the degree of substitutability between the different intermediate goods increases, moving all the way back in the limit to perfect competition. Okay, now let's turn to the intermediate goods producer, right? Because we still need PIT and YIT, otherwise the aggregation formulas don't help us at all. They are conditional, of course, on knowing the price and good of the intermediate good across all these continuum goods. Now, you may already anticipate, even though we seem to have some heterogeneity across firms, if we have such a continuum of firms, is it going to be realistic that they're all going to be substantively different? Well, maybe realistic in terms of thinking about from the perspective of the real world economy out there, but of course this would be an enormous computational task, right? If we had to keep track of each and every firm individually. So for the ith intermediate goods producer, instead we will presume that they all have the same production function. And so in that sense, they are representative, right? This is kind of a seeming heterogeneity. But in reality, each intermediate goods producer is the same because they have the same production function. And of course, you saw before, right? We have just one lambda f parameter. And so from that perspective, it looks like they are different, but in terms of production technology, they are going to be the same. There's going to be one important heterogeneity that will refer to the price. We'll come to that in a second. But first, the production technology, right? As I said yesterday, if we added the capital stock to this model, this gets a bit too involved. Not impossible. On the problem set, you will find a model that has a capital stock added into. You get a larger number of optimality conditions. I'm very sure you can still manage that, but for now, let's just work with the lower dimensional equation system. If I keep out the capital stock in the end, you will see I'm going to have three equations that I need to keep track of. If I added the capital stock, you'll see it in the problems that I think on top of my head you're going to end up with 9 equations rather than 3. So 3 is much more practical, right? So we have a production function. In short, that is only in labor hours as the factor input. NIT is, of course, from our households, the labor that they supply to the intermediate goods producing firm. And just like in the real business cycle model, we have the technology/productivity shock. Right? That was the key shock in the real business cycle model. We tried to stress yesterday that in the real business cycle model, it's indeed the only driver of business cycles that as productivity improves, that people shift their labor into that period where you have relatively high productivity into temporary substitute labor. With high wages, we have more capital, output expense, but then when productivity falls again, they substitute back towards more leisure. So we'll have this technology shock. That was the core shock and the only shock in the real business cycle model. You already know this is not going to be the only shock, right? Because we also have already a shock to preferences, the demand shock as well. So for sure, the technology shock is not going to be the only driver of business cycles, but it remains one of the drivers of the business cycle model. So I have to link that back to the new business cycle model that we had yesterday. First order autoregressive process. I follow here the setup that you'd find most commonly in the literature, but don't take that unit root too literal. If you had a unit root in this technology shock, this would make some things a bit complicated. We want to think of these fractional deviations from steady state. Right? If we had a unit root, it could potentially become ever larger, those fractional deviations from steady state, because at least we know in variance why the unit root process is having unbounded values. So in practice, people, I think all the time will want to have a rho A that is less than 1, but nonetheless, at least the implementation that you find quite often in the literature that initially the argument could also have in it, but for all the reasons just discussed, that would make things yet more complex. All right, this is our intermediate goods producer. That intermediate goods producer takes aggregate output and the aggregate price level as given. Just think of the intermediate goods producer being too small relative to the aggregate amount of production, so that from that perspective, that's a natural thing, that they take the aggregate price level, the aggregate output as given. Now, what we want to have as another novelty in this model, and maybe even, for sure actually, even bigger novelty than this preference shift that we had introduced before, this preference shock, is we want to go away from flexible prices and wages. Because a model with flexible prices and wages simply doesn't match data at all, right? I mean, that was observed a long time ago by Keynes, by Phillips, and so forth, that the prices and wages are sticky. They don't adjust in fully flexible manner. What this model has as a device to introduce sticky prices is again a very abstracting idea. That idea comes from Guillermo Calvo, an Argentine economist who's actually most famous for his work on international capital flows to and from Southern American economies. That he worked on issues of sudden stops, reversals of international capital flows to Argentina, Brazil, and the like. And the anecdote that I now tell you is not made up, because for a good number of years, Calvo was a colleague of mine when I was at the University of Maryland, so I know him a bit. And what I do know is that even though nowadays he's most well known for this abstracting device, how to introduce sticky prices into the DSGE, National Business Cycle setup, he never thought of this as his major contribution. To economics, he would have always thought that his work on, again, international capital flows to and from South Latin American economies is his most substantive piece of work. But that's what sometimes happens, right? When you do work, the one that you actually didn't think this is such a huge contribution ends up a huge one. And this is a huge contribution because this is the default device in UK and DSGE models to get sticky prices. What is the idea? Really an abstracting device, right? Not a real world depiction. The abstracting device is that in each time period, every intermediate goods producer, I, is taking part in a lottery. If you win the lottery, then you can change your price. And winning the lottery occurs with probability 1 minus beta. Beta is a model parameter, just depicting that probability of winning or not winning the lottery. That is, beta itself, of course, is the probability that you do not win the lottery and that you have to keep your price unchanged. Once more, do we observe that in any economy, that firms register for a lottery, whether or not they can change their price? I don't think so. And I'm sure that is not a depiction actually of any economy, advanced, emerging, developing. It's an abstracting device. Because it's basically going to mean, right, when the firms can reprice, it will act as if under flexible prices. Right? So there's going to be a portion of the pricing that's like in a flex price market. But there's also going to be a portion of the firms that cannot reset their price. They must keep the price to the previous period. And as we know, right, from our all-regressive models, what does it mean when you have a lag-dependent variable on the right-hand side? It introduces persistence, right? This past price propagates, right? And so that's going to introduce price rigidity, limited adjustment of prices. If every intermediate goods producer was winning the lottery all the time, right, they reprice with probability 1, beta is 0, we are back to flexible price. But that's what we want to avoid, and have this artificial device that while some intermediate goods producers can reprice, others cannot. They stick to their past price, and therefore we have price rigidity. There have been lots of attempts in macroeconomics to explain why prices do not show fully flexible behavior. One prominent hypothesis are also so-called menu costs. That comes out of the 70s, and then, the main story that people would tell, well, if you think about the owner of a restaurant, it costs them to change prices and print a new menu that they distribute to their customers. Right, so that it would be literally costly to change prices because you had to reprint your menu. And nowadays, there's many restaurants, right, also that basically just give you a tablet or something, And so all that they have to do to change prices is hit the button on the laptop that basically runs the software that's displaying the menu. Not costly at all to change prices, right? That physical cost that's maybe still here or there. The case, of course, some restaurants also play tricks, right? Rather than reprinting the whole menu, they put a sticker into the menu to give you the higher price, so that you can't see the old price anymore, but you can see the new price. That's probably also not that costly, right? To put a sticker into your menu to indicate the higher prices. So menu costs were very popular for a long time, but it also is realistically nothing but a bargaining device. And so Calvert thought of a probabilistic scheme where the firms take part in a lottery, and if they win that again, they can reprice them, otherwise they must keep the price unchanged. But of course, again, this is not that you would now try to find some economy where that is literally happening like that. It's not, it's an abstractive device to introduce limited degrees of price flexibility. Also, of course, understood from the perspective that theta is the probability of not winning the lottery, not being able to reprice, and 1 minus theta is the probability of winning. Then theta, 1 over 1 minus theta, is the average number of time periods for which a price does last. Okay, now we need to look next, and that's perhaps the most convoluted, algebraically challenging part of such a model. We need to look next at what are the optimal price decisions of those firms that win the lottery and can reprice. Well, it's not as simple as in the RBC model because we are not operating under perfect competition in general. Lambda F in general is going to be larger than 1. We have some degree of pricing power. There's some degree of input. Right? So now we need to derive the markup on marginal cost that the intermediate goods producer will charge if he or she is allowed to reset the price. Okay, so what do we have in 20? In 20 we basically have what you might call the value function of the firm. I in period T, what is that? This is just the conditional expectation that you form at time t. Suppose you reprice in period t because you won the lottery in period t. And then, of course, first of all, we need to discount any future time period. We already had yesterday, right, this stochastic discount factor that we used in the no Ponzi game condition, right? There we had this no Ponzi game condition. This stochastic discount factor as the product of the deterministic discount factor times the ratio of marginal utilities in the future period under consideration relative to the current period. Given that the households own the firm, that should be the same form of discounting, right? The households and firms of the future, and that includes that. This is therefore just the overall stochastic discount factor for period T plus 1. Now, what do we have in the fraction at the end? Just profits. Profits, because first term is nominal revenue, right? The price that the item intermediate goods producer charges in T plus K times output sold, minus that the script C is denoting the cost of producing output. We'll get to that cost in a second, but for now just in a generic notation, the cost of producing the amount of output YIT or YT plus K that you sell at time T plus K, divided by the exit price level. Right? That of course the intermediate goods producer remember takes as given in T plus K. Right? So this is real profits rather than nominal profits. You want to maximize, of course, real profits rather than nominal profits. Okay, now these are in the numerator also the profits that before in the household budget constraint we call the dividend, right? This is here synonymous terminology. Of course, I understand in finance you would not equate profits to dividends. That's a different thing. Once the firm has profits, it decides upon what is the level of dividends that it wants to give to the shareholders. But in this model, it's a synonymous, so now we finally also have where the D comes from, right? That D is, of course, aggregated across all intermediate goods producing firms. What are the dividends, in other words, within this model, the profits that the households as owners of the firms collect across all intermediate goods producing firms. Okay, now to the cost function. What is the total cost of production for intermediate goods producer I in period T plus K? That is the amount of output produced multiplied by marginal cost. Right? Marginal cost is just the cost per 1 unit of output produced. Then this is the total cost. What is the marginal cost? Think back to our production function. We only have as the factor input labor. What does labor get paid? Wages, right? So of course the marginal cost is higher, the higher the wage that the firm has to pay. But it's not just the wage, because the marginal cost, of course, also will fall if productivity increases, right? Because for a given wage that you pay for a given number of labor hours, you simply get more output because the productivity of our employees is higher. So the marginal cost is not just the wage per hour of labor, but the wage adjusted for productivity, right? That's the marginal cost, simple expression in this production function that we had in 17. Okay. Now this looks still like a quite formidable optimization problem, right? To set up and solve for. And per se, of course, right? If you think about the construct that we had, this lottery, of course, per se, there'll be lots of different histories, right? When exactly each and every intermediate goods producer wins or does not win the lottery. So this seems a really difficult optimization problem, but how can we simplify it a bit? That's going to explain in 21. 21 basically says, okay, so let's keep looking at those intermediate goods producers who won the lottery, who can reset the price. What is for period T plus K, right? Taking out of the sum that goes across all current and future periods, that is from K0 to infinity, let's just take out one specific K to look a little bit more closely at what is this expression that each and every firm has, the conditional equation at time t of, we call lambda. Capital lambda is that stochastic discount factor, right? Just shortcut notation for that stochastic discount factor that from the perspective of period t, we form with respect to k periods ahead, period t plus k. So what is that expression of the discount factor multiplied by the dividends that the firm collects in period I rendered real by dividing by the average price level. So now we start to think about what are the partly different histories and the partly different futures in particular also if you have won the lottery in period T. Lots of possibilities, right? You may win the lottery again right away in T plus 1, and you can reprice again in T plus 1, and maybe if you're super lucky, you win it again in T plus 2, and you can already reprice in T plus 2 again, but of course there's lots of different scenarios that you may not win the lottery again in T plus 1, not in T plus 2, for many periods you may not win it, right? It seems really tough to account for all of these scenarios, but it's not that tough, and that's what 21 explains. So what 21 says is, maybe let's start with the second part, that you were not winning the lottery in period T, Right, so that is the 1 minus, so that we were careful again, not to confuse myself, let's use the same setup as on slide 11. Right, with probability 1 minus theta, you win the lottery. With probability theta, you do not win the lottery. All right, so if I look back at my expression in 21, let's maybe start at the beginning. Theta to the power of k means for k periods, I will not win the lottery. For k periods in a row. Theta times theta times theta, theta to the power of k. If theta is multiplied k times first k times, I do not win the lottery. What does that mean? In that case, the price that I set today in period t is still going to be the price that holds in t plus k. Right? So in that sense, it's particularly important to get the price in t right. We'll always want to get it right. But in this scenario, of course, you know, right, that the optimal price that you set in period t, let's note that pt star, is still going to be the relevant price holding in t plus k. Now, what about the alternative? Right, this now refers to the situation where you win the lottery after period t again. Right, and in particular says we have situations where you were winning the lottery over all h times, 1 minus theta times 1 minus theta to the power of h minus 1. You were winning the lottery h times, and k minus h times you were not winning. So that overall, of course, this is again h plus k minus h going forward k periods to period t plus k. If you win the lottery again, and that's why I put this 1 minus theta in front of it, at least once the price that you set in period t is not going to bind you anymore in t plus k, right? Because you were repriced. If you win the lottery at least once after period t, for period t plus k, the price that you set in period t is not going to constrain you because you can reprice. Right? And so what the important part here is all those scenarios where you, after period t, win the lottery at least once, you don't need to keep track of because they don't matter. Right? Because I know already in t, if I win the lottery at least once again in t plus 1 or later, I can reset the price. The price that I set now doesn't constrain me. So I don't need to bring that into my optimization. And so that's going to dramatically simplify 20 if you plug back in 20, which says we basically only need to look at those scenarios where you don't win the lottery again. Of course, it was all k periods, right? Still, of course, for period t plus 1, t plus 2, t plus 3, all the way into the infinite future. That's the only scenario that matters. That you, after period t, never win the lottery again. Because then the price, pt star, that is set in period t, is going to bind you in all those future periods. Okay, now, 22 plugs that in, right, from 21, that we only need to care about those scenarios where after period t, you do not win the lottery again. So if you now maximize the objective function in 22, it looks already a lot more tractable, right, because we don't have to look at all these different scenarios that could possibly unfold. Subject, of course, to our demand constraints that we had from before, right? 23 is just putting into period t plus k the demand function that we had in 15. So just as, for each period t plus k, I want to maximize this objective function subject to the demand for my absolute good. that the overall final goods producer, the aggregator across those intermediate goods, has for my height intermediate good, but of course we know that's the same across all firms, right? Because they use the same production technology, they have the same parameter lambda f, so they all have the same demand. So this one demand factor is sufficient. Okay, and now, if you're algebraically curious, I would say feel free to check 24, that it's correct. If you say, I don't need to do every little piece of algebra, then I think you can spend your time more wisely on other things that come first for doing this algebra. In any case, you get an expression for the optimal price at time t, intuitively as a function of output, egged output, right? Because the egged output matters for how much is demanded of the ith intermediate good, as a function of the marginal cost of production, as a function of the exit price level, right? Because the exit price level also is important for what is your relative price at which the final goods producer purchases from you, the intermediate goods, and these stochastic discount factors. Of course, all of that here multiplied by the one and only scenario that matters. Again, across all future periods, never win the lottery. That gives you the optimal price. That's in 24. Right? So if you're happy with that intuitive description, why those factors should be in there, for me that's good enough, and we don't want to spend an extended period of time to do the algebra. Yes?
So, slightly before that, so it's just like the intermediate goods producer trying to maximize, like trying to set the price, because like for each period they have, that person will not have a chance to set the price.
Exactly.
So they have to think ahead of time
Exactly.
to generate.
Exactly. That's the point, that if you know you're never going to win the lottery again, then you know the price that you set in T is going to constrain you up into the infinite future. And that's why it's an intertemporal optimization problem, but all those scenarios where you know that you're going to be able to reprice, they don't matter. Right? Because from that point in time, you just look at it again, at this value function, in that time period where you're allowed to reprice. So you can ignore them in this decision-making problem. That's why this device has become so popular, because it looks at first like, right, we have a setup that's very realistic. Each and every different firm has a different scenario as to when it reprices and when not. But in terms of solving it becomes like the problem of a representative firm that in setting the price in T only cares about that one scenario where it will not win the lottery again in T plus 1, T plus 2, and any other period thereafter. So it becomes still algebraical, again, a bit convoluted, right? Of course, to take that first order condition and solve it for PT star, but much more tractable than we would expect. At the outset, when we have such a continuum of firms that per se each and every one has a different scenario as to when they reprice. That's the beautiful thing, that per se you have this whole distribution of firms that reprices at different points in time, that has different numbers of periods, how long the price is going to be sticky, persistent, right? Because for each and every firm you have a new draw in each period as to whether or not they win the lottery, but at the end it becomes the decision-making problem of a representative firm. Good pricing. And that's why this device of Calvo, this lottery, win or do not win the chance to reprice, has become so popular. Okay, now if you plugged into 24 the possibility that theta was 0. If theta was 0, that means that 1 minus theta is 1. So in each period with probability 1, you win the lottery to reprice. That's fully flexible prices. And what must be true in fully flexible prices? We must have that we set the price in each period as a markup amount. And what is the markup? That's governed by our parameter lambda f, right, which you recall was our parameter measuring the degree of substitutability between the different intermediate goods. And as we argued on slide 10, that therefore gave us the pricing power of the intermediate goods produced. Right? So the markup is just this lambda f. Remember, it has to be larger than 1, this lambda f, because as it converges to 1 from above, we go to perfect competition. So if lambda f was 1, no intermediate goods producer has pricing power, we're in a perfect competition, we get at prices equal to marginal cost. We're back to the new business cycle. Right? Then of course we would need this whole setup, then we'd rather work with our little business cycle firm structure from yesterday. That's still a special case, right? That you were winning lottery as each and every intermediate goods producer. You have flexible prices, and on top of it, lambda f converges to 1. And if it is 1, we have a perfect competition and prices equal to marginal cost. Okay. So, but of course, that's again just a special case, and if we want to focus on the special case, we should rather stick to our real business cycle model. Production function and production technology from yesterday, much easier to handle, of course. So, of course, we do think that lambda f is going to be larger than 1, so that we have pricing power of those firms, markups are going to be. In regards to aggregate prices, well, we need to aggregate right across those firms that were repricing. 1 minus theta is the probability of repricing, so out of that continuum of firms from 0 to 1, right, 1 minus theta is the fraction that does reprice, for which BT star is a relevant price, and for the remaining fraction of firms, of course we know that they keep the price, that is the price of BT minus 1. Aggregating across all firms, you get the aggregate price level, and that's the formula in 27. I noticed that this is, at first when I read this again, I thought maybe there's a typo here, that the theta is missing, but that's correct, because here we are integrating, right, across all those intermediate goods producers who do not get to reprice, and that's a fraction theta, and that's where the theta comes from, but this is here correct, it's just denoting that we integrate across all those firms that do not get to reprice, and that gives us that expression for that integral in 26 as the first term in 27. So we have the price level for this economy worked out as well. Further fine-tuning, right, what we had before for the aggregate price level, before we just said it's integrating across all intermediate goods producers, but now we know a little bit more about the pricing structure, so we can further fine-tune 16 into the form of 27. A bit nasty algebra 2 is, given that in our model we do not want to have the price level, but the rate of inflation. Why? Because after the break, as the last component of this model, we are going to introduce a central bank that's going to be inflation targeted. Right, and so we want to convert everything from those price levels that we have in 27 to rates of inflation. I don't know, maybe you don't find the algebra nasty and you say, once you do it, what did you talk about? This was most simple thing. But for me, at least, it's too much algebra to do it explicitly here. And so just the result upon dividing on both sides of 27 by the price in period t minus 1, we express everything in terms of the rate of inflation from t minus 1 to t, right? That is pi t is measuring the rate of inflation, t minus 1 to t. And that's the third sector. So after the break, we'll complete the model with the last part. Let me introduce market topics, right? Why is that crucial for our new Keynes and DSGE model? Because we are still after forecasting the federal funds rate. So in the end, we need to have a federal funds rate in our model, right? And so that will mean we have to specify the policy function of the monetary authority, and that will do the Taylor rule, but let's do the details after the break. Then we'll have the model complete, because they will not need to spend much time on log linearization, because we've already practiced that. So what we'll then do as the lion's share of the first part of the afternoon is I'll tell you more about what we kind of took so far as a black box and Dynare to solve this model. And that's my last sentence, just for you to reflect upon it a little bit before we come back in the afternoon. What's going to be the crucial part of this model that's different from an AR, ARMA, ARIMA, VAR, vector regression model? We have these future expectations in there. If you just think, for example, back to the Euler equation, just to take one equation from there, whether in the nonlinear form or the linear form, this contains expectations at T of consumption. That's an indoor construct. Do we have data on expectations in the US economy in the aggregate on one period ahead consumption? I haven't seen that. In household finance, I think Michael Haliassos is going to talk to you a lot about surveys that he's been very instrumental in, where you measure this and that expectation, and that's very nice and very good. But of course, you don't have expectations across all future horizons in any survey for anything, right? So if you really want to be serious about solving this model, you can't hope that you can just plug in data on expectations. So what we'll talk about then is the lion's share of the first part of the afternoon is how do we solve out these conditional expectations about the future. And that's the so-called solution of a rational expectations model, rational expectation, because these expectations that in its form in our model, right, are the mathematical conditional expectations of the world. And that's so-called rational expectations in macroeconomics. And so first part of the afternoon will be to solve those models, basically get rid of this term, so that we only have terms in counting like variables like in a VR. And so we'll see that at the end of the day, we can write this new Keynes and DSGE model as a restricted VAR with lots and lots of parameter restrictions. Then we can estimate it, then we can forecast it, right? Because we have to say discuss estimation for such VR models. It's going to be a little bit different because it's highly restricted, but per se, that's something we know how to do. Estimate forecasts from VR. So once we have this restricted VR that this model implies, then we can bring it to the data. So don't worry that you think I'm infinitely far away from the end point of calculating forecasts for the federal funds rate out of these new Keynes and DSGE models. I would think we are going to be well able by 4 o'clock to have calculated our forecasts and to have discussed all the relevant methodology. But maybe let's start at 1:05 to make sure that we have the requisite time. Is that okay? Start 1:05 according to this clock there. Then we'll see